Okay, so these are the homework problems from WebAssign for 7.4. The first one, and by the way, I think some of the numbers are going to be slightly different because it randomizes some, but that should be fine. Okay, so the first one says, or number 2 says, the basic equation sine x equals 2 has how many solutions? Okay, so sine of x equal to 2 has either none, 1, or infinitely many solutions, whereas the equation sine of x equal to 0.3 has none, 1, or infinitely many solutions. Well, any equation, any trig equation in the form of like cosine x equals something, 2, or sine x equals 2 will have no solutions if this number, whatever the number is bigger than 1 or smaller than -1. Because the range, the output, or the range of sine and cosine is -1 to 1. So if I'm asking you to solve an equation, let me make sure. Okay, if I'm asking you to solve an equation that says sine x equals something or cosine x equals something, and this output, the 2 in this case, is outside of this range, then there's no solution. Okay. Now, so this one is none, no solutions. Now, sine x equal to 0.3 has infinitely many solutions. Any trig equation, sine, cosine, or tangent, I'll say any trig equation will have infinitely many solutions as long as the output is within the range. As long as the output is okay, as long as the output, and 0.3 is within this range. So, and why does it have infinitely many solutions? Well, because of the nature of this sine graph, right? This sine graph, or cosine graph, or even tangent graphs, they're periodic, right? They repeat. So, oh, that's pretty ugly. But this question is asking, the graphical representation of this equation is, if I drew a line just at 0.3, at a vertical height of 0.3, which let's just say is roughly there, how many times am I going to cross this sine graph? In other words, when is this sine graph equal to 0.3? Well, infinitely many times, right? Because sine is periodic, it's going to keep over and over again. It's going to keep crossing that 0.3 line. And of course, this will be the same for cosine, and even for tangent, which has this kind of graph over and over again. This is a poor representation, but something like that over and over again. So how many times would 0.3 cross the tangent graph? Well, still infinitely many times. So any trig equation is going to have infinitely many solutions as long as that output is within the range. If it's outside the range, then there's no solutions. And this is reflected in when we solve that. How do we reflect this infinitely many part? That's when we add the plus 2k pi for sine and cosine. That's going to tell you that's going to be every rotation. Or in for tangent, it's k pi, because its period is just pi instead of 2 pi. Okay. Number 5 was, let me go look at it. Okay, where is it? Okay. It says solve the given equation, so it says sine of theta is equal to square root of 3 over 2. Okay, so they want us to solve this equation. We could solve for theta by using the inverse sign on both sides, but this is a nice coordinate that we're used to. We could even draw a reference triangle to figure out what angle this is, and let's see, this would need to be 2 and root 3 and 1. This is going to be a pi on 3 angle. Oops. And you might know that just from looking at your unit circle. But that's not the only place that sine of theta is equal to square root of 3 over 2. We can also have it in the second quadrant, where we have this kind of reference triangle. So in the first or second quadrant, and that second quadrant angle will be 2 pi over 3. So I'm looking at these two angles. And this needs to have infinitely many solutions, or it does have infinitely many solutions, because the first solution is here, and then we can rotate around infinitely many times to get to that one angle, and the same thing with this angle, can rotate around infinitely many times, so that's why we add the plus 2k pi to each of those. So these are the solutions for this equation. Okay. And why are there two? Well, because if you look at the sine graph, one period of the sine graph, and I'm drawing some line at square root of 3 over 2, which is, it's less than 1, let's just say it's around here somewhere. It's going to hit twice in every period, here and here. It's going to hit twice in every period, in every cycle. Okay, so there are two base angles, and then every rotation of those base angles. Okay, so the next one is 15, which is tangent of theta is equal to 5. Now, is this in the range of tangent? Yes, because the range of tangent is unbounded, right? Off to infinity and negative infinity. So this is in the range of tangent, so we can actually solve this. But this is not a special coordinate. This is not like square root of 3 over 2 or 1 over 2 or anything like that. It's just some random number that we're not familiar with. So the way to solve this is you use the inverse tangent, and you approximate using your calculator. And let's see, I'm getting 1.37 radians. 1.37 radians. Now, my final answer will be theta is approximately 1.37 plus k pi. So why is it just k pi? By the way, k is an integer. K is an integer. So these are integer multiples of 2 pi. So when k is 0, we just have the base angles. When k is 1, we have 1 rotation. When k is 2, we have 2 rotations. When k is -1, we have 1 rotation going backwards. You can think of it on this picture too. When k is 1, for this angle, I go around 1 more time. When k is 2, I go around twice. When k is -1, I go around backwards. And all of those angles satisfy this equation. And likewise here, I need to add k pi, and I'll say we use k pi instead of 2k pi because tangent has period pi, whereas sine and cosine have period 2 pi. That's why for any equation involving sine or cosine, you'll use 2 pi times that integer multiple, 2k pi. And for tangent, you'll just use k pi. And I'm using approximately here instead of equals because this is something I had to round in the calculator. So anytime you use the calculator and you have to round, you should say approximately. And notice also that there's only one angle, or one like base angle, whereas here there were 2. And again, that's because in each period, for tangent, just the way tangent looks, it's only going to hit once per one of these cycles. It's only going to hit once. Whereas for sine, because this period of sine and cosine is from here to here, or at least for sine, but cosine's so similar, right? These numbers are going to hit twice per period. That's why for this one there were 2 base angles, but for this one there's only 1. Okay, number 27 is next. Okay, this one says square root of 2 sine theta plus 1 is equal to 0. Okay. So the idea with this one is to solve for sine theta so that we have an equation with just sine theta equals a number. So sine square root of 2 times sine of theta is equal to -1. And then sine of theta is equal to -1 over square root of 2. And then we could rationalize the denominator and get that sine of theta is equal to negative square root of 2 over 2, which we recognize as a nice coordinate. It's one of the 45-degree ones. And where is sine of theta going to give me a negative square root of 2 over 2? So you can consult your unit circle, and you should see that it will be these 2 angles, both pi on 4 angles. This one will be 5 pi on 4, and this one is 7 pi on 4. So those are the 2 base angles. So my answers will be theta equals 5 pi on 4 plus 2k pi. Or what is it asking? Yeah, find all solutions. Okay, just making sure. And theta is equal to 7 pi on 4 plus 2k pi. So two different answers there. I think when you're entering these in WebAssign, you need to make sure that they may not have 2 separate boxes, so they're going to want you to write it like this, comma, and then 7 pi on 4 plus 2k pi. And they may even want you to order them from smallest to biggest angle. Okay. Okay. Let's see. Oh, I think I went out of order. 26 is next. So this is just two different ways of writing the same answer. Just two separate thetas, or a comma, separating them with a comma. Okay. 26 is next. It says sine of theta plus 1 is equal to 0. So we need to solve for sine theta. So sine of theta is equal to -1. Now, where is sine of theta equal to -1? Is that a number on our unit circle, or are we going to need to use the inverse sine function? Well, it is a number on our unit circle, right down here at 0, -1, where the angle is 3 pi on 2. And that's the only one that yields a -1 for this y-coordinate on your unit circle. So that means theta is equal to 3 pi on 2, and that's it, plus 2k pi. So there's just one base angle this time, and I'll explain why. Because usually sine and cosine should have two base angles, and tangent's the one that only has one base angle. So why does this one only have one base angle? Well, if we look at the picture of the sine graph, this is 1 to -1. There's only one number that I can pick that's in the range of sine that's going to hit one time per period. Or there's actually two numbers. It's either 1 or -1. Because if I pick -1, it's supposed to come down here and hit there, then it's only going to hit once per period. See, this is the period right here from 0 to 2 pi, and it's only going to hit once. That's why there's only one angle that satisfies, or one base angle that satisfies. Of course, there's infinitely many because of the plus 2k pi. Every time I rotate around, I can get another solution. But the point is that -1 and 1 are going to be the only two places where, for a sine or cosine graph, you have just one base angle. The rest of them, all these numbers in between -1 and 1, you'll have two base angles. Okay, number 43 says, oh, I lost it. Where is it? Oh, plus 2. Okay. So, oh, no, I messed this up. It shouldn't be 7 theta. Yeah, okay. It's 3 sine squared theta minus 7 sine theta plus 2 equals 0. So this is a quadratic function with sine theta playing the role of the variable that's being squared. And so what we can do here is rename sine theta as x to make this seem more familiar. So we'll have 3x squared minus 7x plus 2 is equal to 0. This is just a temporary step just so that we can solve this quadratic function and get two separate equations of sine theta to solve. And it's going to be easier if it's written in a more familiar form. So I've replaced sine theta with x here. And now I need to factor this somehow. Let's see, I'm just going to try to factor it just by looking at it. Let's see, both needs to be negative. So if this is a 1, no, this should be a 2, and this should be a 1. Okay. And then setting each of these equal to 0 separately, and then solving each one. Now replace x with sine theta, so I have two equations. Sine theta equals 1/3 and sine theta equals 2. But this one is undefined, or we should say no solution, undefined or no solution, because it's outside of the range of sine, because of that 2. This one is defined, but it's not a nice coordinate like 1/2 or square root of 3/2. It's close, it's 1/3, but what we're going to have to do here is actually use the inverse sine function and use our calculator to approximate. And I'm getting theta is equal approximately 0.34. This is in radians. But there should be another angle, right? This should yield 2 base angles. So let me draw a little picture of where is sine positive. Sine is positive in the first quadrant, which is where this 0.34 is, roughly over here somewhere, and there should be a corresponding one over here in the second quadrant. But if this is 0.34 radians, how do I find this angle? How do I go all the way across? Well, all the way is pi, and then I'll take away 0.34. That's how I find this angle. And that's going to give me roughly 2.80. So the other base angle is 2.80 radians. So my final answers will be theta is approximately 0.34 plus 2k pi, and theta is approximately 2.80 plus 2k pi. There we go. Those are my 2 base angles, and then my infinitely many solutions for each, infinitely many rotations for each one. Okay, so next is 7.5. 7.5. Number 3.